Okay, greetings students. This is the lecturer, Mr. Ramnath, and I'm going to outline how to solve the test 1, question 1. Question 2 is straightforward, so I'm not going to worry about it. So in any case, you've got a mass, you've got a crank, the mass is connected to a spring, the crank is connected to a damper. You need to deduce the system and the damping ratio. So let's draw a diagram and then we can take it from there. Okay, what do we have? We've got a crank connected to a mass connected to a spring connected to a ground this is one crank, and then this is connected to a damper. This is a pivot which can rotate. There is a spring constant, there is a damping constant, there is a point B, there is a point A, there is a pivot, and we are given that the mass is displaced distance x in an upwards direction. So for convenience, I am going to put the y-axis in the opposite direction. If it moves up a distance x, it would then rotate a small angle theta in that direction and in that direction as well, where the length is a and the length of b is, well, OB is that, and the angle is 90 degrees. So using the definition of angle is arc length over radius, it follows that theta, if this point A moves up by x, that would be approximately, x would be an approximate arc length divided by this, which would be A, and in addition, theta, if point B moves a distance s, theta would be s, which is the arc length on the other side, divided by the radius, which would be b. Equating them, it follows that x over a is equal to s over b, therefore s is equal to b over a times x, and that would imply that s dot is equal to b of a x dot. If m is the mass, it moves up to x, the displacement would be the displacement of a. So the spring force is going to be minus the spring constant times x. Now, if this moves up a distance x, this would move theta in the counterclockwise direction. That would stretch point B a distance of s, and then it follows that the force would be minus the damping constant times the velocity of B, and then that would be minus c into. Now, here's the trick. This is your point A. This is the point B. If x is moved upwards by x, if point A is moved upwards by x, that's a positive direction. So this would go in that direction. It would rotate. Now, if this rotates, this would then also rotate as well. So it is moving in this direction, but this is a negative direction because positive y we assumed is towards the left, and then point B is moving towards the right. So the direction of the velocity B is actually minus B over A x dot, which is then positive BC over A times x dot. In other words, that means this is it means the damping force is in this direction and spring force is in that direction. So if M is moved upwards by x, it would stretch the spring, and the retarding force would be in the opposite direction, so the spring force is downwards. If M is moved upwards by x, it would rotate this in the counterclockwise. This would then move in the counterclockwise, so the motion would be towards the right. So the velocity is towards the right. And then the damping force would be in the opposite direction to the velocity. So the damping force would be towards the left. So the torque caused by the damping force is force times perpendicular distance, which would be Fd times B, which would then be B squared C over A times x dot, and that would be in a clockwise direction. Now, this means the torque is in a clockwise direction because of the damping force. I'm moving it upwards. It moves the point B towards the right. The retarding damping force is to the left. The force acting in the left induces a clockwise torque. And then we have at the point O, the clockwise torque is this expression. Now, if we calculate, and let's just call this the left side, and let's call this the right side. If I'm calculating from the left, I must get this answer. If I'm calculating from the right, I must get the same answer. So there would be an apparent force in inverted commas on the right hand side. And that means the torque at the point O should equal to the force times the perpendicular distance, which we know to be B squared C over A x dot, which would then imply that the force dividing by A, then that would just be B over A squared C x dot. And then if we look at the mass, we would have a spring force, we would have an apparent force. Newton's second law would then give us m times the acceleration is equal to minus kx minus b over a squared cx dot, because it's in the downwards direction, and then just rearranging, that would be mx dot dot plus b over a squared c x dot plus kx is equal to 0. So m equivalent is equal to m. C equivalent is equal to and K equivalent is equal to K. Therefore, omega n is equal to the square root of K equivalent over m equivalent, which is equal to square root of K over m, and then zeta would be C equivalent over 2m which would be b over a squared c over 2m square root of k over m, which is equal to c over 2m b over a squared square root of m over k. And then that's the answer at the end of the day. So that is the solution to the question 1. What happened? The mass is in translation. It's exposed to a retarding spring force. It moves upwards by a distance. It causes a rotation. The rotation stretches a point. The point is stretched in a certain direction. A retarding force is generated in the opposite direction. The retarding force induces a torque. The torque calculated on one side must equal to the torque calculated on the other side. In order that for there to be equivalence, there would then be an induced force on the other side, to equate to the torque on the opposite side. That force is acting in a particular direction consistent with the direction of the torque. We deduced that force and then we applied vector superposition to work out the resultant motion. We took the leading coefficients as the equivalent mass, damper, and spring values. We worked out the natural angular frequency, and then we applied the formula for the damping factor. And then that is basically the answer to the problem. Thank you very much.